So welcome back to the last session of the DevCon 2022. My name is Michele Scarlatella. I will be your moderator for this session. The session is about the MIPI RFFE for 5G front-end modules, and it will be presented by Florinel Baltenot from Skyworks Solution. Florinel is a technical director with Skyworks Solution in Irvine, California. He's presented short courses and tutorials as an invited speaker at the IEEE Microwave Theory and Technique Society International Microwave Symposium and Asia Pacific Microwave Conference. He holds 77 US patents with several more pending. He's author of the chapter Envelope Tracking Technique in the EET, a book, Radio Frequency and Microwave Power Amplifiers, Volume 2, Efficiency and Linearity.
Thanks everybody for attending the session. My session is going to be about MIPI RFFE for 5G front-end modules. The outcome, the agenda for this session is about 5G deployment, solution for 5G RFFE control, 4G, 5G MIPI RFFE control in version 3.0, 5G mmWave challenges, which is going to be a little bit new for MIPI, and at the end, references. MIPI RFFE has been de facto standard for RF control in mobile devices, including smartphones, tablets, and other mobile devices. Multiple versions of the specification have been adopted to ever-evolving 3GPP wireless standards. MIPI RFFE 3.1 is on track to be released later this year in 2022. So, in terms of deployment, you probably remember that 5G arrived in smartphone first in the United States in 2020, so we have almost 2 years. And with the arrival of 5G, the smartphone interfaces are becoming more complicated and is going to get even more complicated with the next generation's smartphones. If we look back into MIPI RFFE history, so the first release was 1.0 in 2010, and I remember from that year that at that time there have been so many customized standard interface. I mean, I'm old, very old with this industry to remember. I have so many meetings just to figure out how the communication between different transceivers and the front-end module is going to be done. With the adoption of MIPI RFFE, we achieved a very good standard, and definitely with the smartphone development, the MIPI RFFE has been evolved, and we went through version 2.0 and recently 3.0 and soon to be released 3.1. So MIPI RFFE development has followed the module device evolution. With adoption of the variant 3.0, MIPI RFFE has adapted to 5G sub 6 GHz requirements. Sub 6 GHz are called sometimes FR1, and FR2 is about mmWave. And talking about mmWave, with the adoption of mmWave and deployment for FR2, there are new challenges which has to be addressed by MIPI RFFE. So when it comes to MIPI interface, initially we had one main interface, one master, and up to 16 subordinate interfaces. Recently, because there is, with the 5G adoption, there is not just one transceiver, there are several transceivers on the phone board. we have been required to have more than one main devices. So each main device can take control and control up to 15 MIPI subordinate devices. So each RFFE bus can support up to 4 main and 15 subordinate devices. At any in any given point in time, one main device has the bus ownership and is responsible for bus management. Operation of MIPI RFFE bus, while our activities are on, should be guided by required EMI limit bounds. And that's an interesting comment, because I remember back in 2010 when we started using MIPI, was on a good main feature that the MIPI clock to be active only on data has been sent on or received. These days, with the EMI shielding techniques, MIPI bus and the fact that there are so many devices is very active. So we have to take our our methods to have a good EMI rejection. So one of the few things which I would like to mention is the fact that with the adoption of 5G and transition from 4G to 5G, we have two scenarios. One is so-called standalone, where 5G is a standalone system. But mainly for the real life these days, we have non-standalone system where there is a coexistence between 4G and 5G. Now, NSA 5G, so non-standalone 5G, actual deployment comes with dual connectivity. That means we keep the 4G legacy, and also we use 4G as backbone for signaling. What's interesting is that for example, this year at the Mobile World Congress, few companies shows a demo with up to 2.5 gigabits per second for standalone 5G and FR1. I mean, if you're gonna see in my next slides, when it comes to 5G, one of the metrics is to have data rates higher than 1 gigabit per second, and definitely this was an experiment where has been shown that using under 6 gigahertz spectrum, we can achieve 2.5 gigabits per second. Since I prepare these slides, I have seen recently an announcement somewhere in Asia that it was a demo for 5G NSS standalone using millimeter wave with 4.5 gigabits per second. But probably I will spend a little bit more time at the end of the presentation about this stuff. Now, when it comes to 5G front end, I have this probably very busy schematic diagram. And this is just to show how complex is RF front-end module into a smartphone device. There are 6 to 8 antennas into a smartphone device versus 2 or maximum 4 antennas. 4 years ago, even I have seen for the next years, people are talking about 9 antennas or 10 antennas. Each antenna, in theory, has to be reachable by any TX-RX channels. In theory, in reality, not all of antennas can be reachable. And for this reason, there are several 6-7 MIPI RFFE which are working in parallel. If we multiply this number 6, 7, 8 or whatever with the number of smartphones sold in a year, we realize how many MIPI interface and how used this standard is in this environment. When it comes to 4G, 5G RF frequency bands. We have especially the low bands, which are reallocated for 5G, but also we have new bands like bands 77, 78, 79, which are in 3.5 gigahertz spectrum, which are mainly 5G bands. And uh, I'm using this slide because for 5G and under 6 gigahertz band is still the main 5G data pipe. 5G comes with also more radios working on the same time, and for this reason, several FEM active and there are several front-end module active, and therefore there are several MIPI RFFE bus instances which are also active. To give you an example of MIPI RFFE and where MIPI RFFE is present, I used iFixit smartphone teardown, and you can see that these days the smartphones are full of integrated chips and full of transceivers, modems, application processor, but also a lot of front-end modules. I did a kind of a screenshot and show where the MIPI RFFE is located into that. I guess hopefully it's a Skyworks product, can be also Corvo, Broadcom, and other companies working in this area. So, and you can see that in theory, there are so many RFFE, MIPI RFFE bus interfaces used for this dies. What's new in this world is the fact that unfortunately we feel the under 6 gigahertz spectrum. I have seen discussion, and probably we're gonna move also into under 10 gigahertz spectrum is called FR2. Still the discussions are in incipient phases. But what's more kind of recent is the fact that smartphones 5G are trying to move into so-called millimeter wave FR2 frequencies. And recently, 3GPP release 17 introduced higher frequencies, like frequencies around 57, 71 gigahertz, and carrier aggregation. That means we're gonna use carrier aggregation for millimeter wave. From this perspective, and MIPI RFFE bus will continue to play a big role for RF front and control over these bands, with definitely some challenges, which I'm gonna show in the end of the discussion. Talking about 5G, probably we all hear about this buzzword 5G, and the main thing 5G is promoting, but it's not the only thing, but the main thing 5G is promoting is high data rate. So I did this diagram, which is a little bit busy, but I would like to show that in order to achieve data rate higher than 1.2 gigabits per second, unfortunately, we cannot use just one data pipe. We have to use MIMO. We have to use, in this case, 4 channels, downlink channels. And on top of that, for uplink, in order to support this data rate, we have to use a speed which is higher than in this particular case, with 77 megabits per second, which requires 1 channel or sometimes 2 channels for TX, or even 3 channels for TX. That's put a lot of challenges for RF front-end in terms of RF design and performance, but also adds a lot of challenges for MIPI RFFE. And I would like to jump a little bit on the very theoretical and philosophical in a way side that you see always in RF we are in communication or are based on the fact that we need more data rate, higher data rate. And this is based on the Shannon theory. Shannon theory, and I put that formula for Shannon, I think it was around probably 70 years ago. Shannon theory has, what doesn't show in this formula is the fact that assumes an isotropic system. In reality, we deal with systems which are anisotropic, are not the same. So in order to make the Shannon theory happening, we need time alignment. So every signal is coming and we have to align these signals. This is one reason why probably we have seen that when we jump from 2.0 to 3.0, we needed that the MIPI RFFE, we needed to react fast. We introduced time triggers and mappable triggers. So as I said, I mean, from the very basic and philosophical point of view, if I can use this term in analog/RF design, these are based on the Shannon theory. Next, it's one of the examples of the MIPI RFFE use where MIPI RFFE is in a complex system. So for example, this is a case where we want to calibrate for envelope tracking, and MIPI RFFE does interface with the front-end modules, but also we have interaction with the transceiver and application process and the modem and application process. So it's a complex system, and MIPI plays a big role in order to do the calibration, in this particular case for envelope tracking. And I put a number here to realize that how precise we need to calibrate this system. So for example, in order to calibrate this system, we need a delay calibration which has to be around less than 0.5 nanosecond, 0.5 and 1 nanosecond. So the calibration is very small. I mean, you see, if we compare with this delay calibration with the speed of the MIPI, we realize that, yes, indeed, the MIPI clock probably it's slower than the delay calibration. And this figure shows also what involves what kind of systems, what kind of circuits are involved in MIPI RFFE calibration. So we are talking about modem, we are talking about application processor, we are talking about several transceivers, and definitely several front-end modules, and I will include antenna tuner here also. And definitely on the transceiver side, we have so-called observation receiver, which takes care of the signal coming from the antenna, and we sense that signal when we do calibration. I mentioned that in order to achieve a high data rate, we need MIMO. We cannot just rely on one channel, and that's one of the things where we need to use several MIPI in parallel. And I did show you on the right side how let's say UHB for band 77, 78, 79 front-end module looks, and definitely you can see that there are two MIPI RFFE working in parallel for that front-end module. The reason for that is because we don't have enough bandwidth to control everything with just one RFFE. So I think there is one question on the right. I will answer that question at the end, Stefan, if you don't mind. So when it comes to MIPI RFFE, as I mentioned, due to these requirements, especially timing requirements, in version 3.0, we have time triggers. So also initially, I remember for version 1.0, we had just 3 triggers, and at that time we said, oh, probably 3 triggers are good enough. In 10 years, we discovered that we need more triggers and we need time triggers. And the theory behind the time triggers, as I explained in my previous slides, is the fact that we need fast response in certain instances. And in order to do that on a bus like MIPI RFFE bus, where the information is sent sequentially, we load so-called shadow registers, and the information transfer from shadow registers to active registers, it's happening when we time trigger, when we write into a time trigger register, and it's done instantaneously when we do that triggering. This is another more detailed slide which shows how the time trigger is happening, and we have a register for a mask trigger. So when that mask is 0, the information is sent from the shadow register to active registers when the counter goes to 0. Otherwise, the information is transferred directly from the MIPI registers to the active triggers when that mask trigger is not activated. Another thing is the fact that with this complexity, we sometimes we want to change when the triggers are happening, and with just time triggers, we cannot do that. So in version 3.0, we introduce mappable triggers, where we can map these counters. We can map this trigger function to different counters, and definitely we can have a different configuration. You're gonna probably ask why that is required. Because it's required because you have to think that a smartphone is a very complex engine. We all want to have a smartphone probably every year. And in order to do that, when the initial design is done, you don't know all the details. So you would like to have a little bit of programmability for different user cases. And this is a reason, one of the reasons, not the single reason, why we like to have mappable triggers. Now, when it comes to millimeter wave, before that, I would like to make a little bit of comment here. One comment is the fact that you see all this functionality, and definitely we can talk about more functionality for RFFE, MIPI RFFE, comes with some prices in terms of die size. If the modems and application processors have moved to very advanced technology like 3 nanometers, and this is where the industry trends goes. The transceivers, they've moved to 7, 14 nanometer FinFET. Unfortunately for RF front-end, which has several CMOS and SOI dies, the technology is still into 0.11, so 110 nanometer, 130 nanometer, with a little bit of 90 and 40 nanometer, but still the digital is at these nodes. And from this perspective, any new functionality introduced, unfortunately, puts a lot of pressure on the size and the functionality of the die. So this adds a little bit of cost, but also adds size. And unfortunately, when we have to add more functionality on a phone board, we need to take into consideration that we have to shrink the size of the die. And that I would like to jump to the new thing like millimeter wave. I will not try to make a tutorial about millimeter wave, but this slide shows how a millimeter wave channel looks into a smartphone. We have 18 or 16 beam forming channels typically in a smartphone. All these front end modules are, I would say, with a little bit of grains of salt, because in actual smartphones there is not a distinction between front end modules and transceiver. But let's say all these front end modules in theory should be controlled by MIPI RFFE, and you can see a little bit of limitation here, because if we are talking about 8 or 16 front-end modules, definitely we cannot control so many with just one bus, so we need several buses. On top of that, we have to do some calibration in real time, and one of the so-called calibration in real time is phase shifting. When we move the phone or we move the smart devices, we have to recalibrate, and in order to do that, we have to do calibration. We have to phase shift to change something into the VCO, or we have to change something into the LNA phase shifting post LNA, or we have to do phase shifting into IF. That's from the perspective of using MIPI RFFE, takes some time, and that's why probably we need several MIPI RFFE. So when it comes to millimeter wave, as I said, we use 8, 16 TRF paths. On TX side, we have up conversion, splitting, phase shifting, VGA, PA, TRX switch. On RX side, we have TRX switch, VGA, phase shifting, combining down conversion, and zero or low IF channels. From this perspective, we have to use, unfortunately, as I said, more than one MIPI, and probably, I guess, I will let definitely MIPI RFFE standard committee debate. I guess probably we need to go higher for the clock frequency. And this is one of the things where I show that the phase shifting is done after LNA. So another thing which MIPI plays a role is that phase shifting does have to change some elements in terms of phase shifting for LNA, but in terms of processing, it's quite complex, because we have to measure the signal to noise interferer ratio at the base station, but sometimes at the UE, so at the smartphone level. And from this perspective, doing the phase shifting, the MIPI RFFE, it's slow, unfortunately. And it's the same thing for the fact that we can do phase shifting at VCO, and people are doing this stuff. And also we can do phase shifting at the VCO in parallel with doing phase shifting at the after mixer at IF. Now, in summary, I will say that MIPI RFFE plays a key role in 4G, 5G front-end control. MIPI RFFE needs functionality upgrades for 4G FR2 front-ends, and probably for FR3, as I mentioned. I mean, there are discussion about FR3. And definitely people are talking about the next generation moving from 5G to 6G. I guess that MIPI RFFE is going to play that role into 6G. Definitely, it's a little bit far. We don't have products, and I don't envision products. And for that reason, we need speed, more speed probably. And we have to keep in mind that the front ends, they don't have just MIPI, they have our digital functionality like calibration and sensors like temperature sensors or other sensor on the front end module die. And This ends my talk, and definitely for other questions, I added additional resources slide where you can find more information about MIPI RFFE 3.1 as well about the 5G front-end module. And I would like to ask to probably answer some questions.
Okay, thank you, Ferdinand. It was very interesting, through on what's happening in the RF. Very complex things that are happening in the RF sections of today mobile ecosystem. Yeah, we do have a few questions coming in. I don't know if you can see. One is in the millimeter wave with the higher SCS. The slot length will become shorter to 8.3 microseconds. MIPI RFFE need to control the RF at short time. How do you increase the control speed with the higher clock frequency, shorten the command length?
Yeah, thanks, Stepan. Thanks for asking me. I think that's a good question. This is one of the reasons why I also at the end of my presentation I put these slides. In my view, we need to increase the clock frequency. Definitely, this is not easy, and we have to be backward compatible with MIPI 1.0 and 3.1 and so on. But I don't see other means to do that stuff. I will say that sometime, as I said, I mean, if we cannot do that, unfortunately, the front-end modules doesn't have to be very complex. I mean, you see, so we have to reduce from functionality of front-end module, which is not desirable, unfortunately. So, as I said, the short answer, yes, to increase the speed.
Okay, there's also a question that I think you partially addressed. Do you see the need to increase the number of subordinate devices to cover millimeter wave?
Yes, I do see. And also I do see the need to increase the number of subordinate devices for base station application. That is, unfortunately, that comes either we increase the subordinate devices or unfortunately use more MIPI RFFE in parallel, as I have shown you in one of my slides. I mean, you see, I can say that I have seen even products in early stage of development, and there are discussion about using 3, even 4 MIPI RFFE.
I think next question you I think also slightly addressed that. What are the noise mitigation methods, considering that the MIPI RFFE clock is active most of the time in the current 5G applications? Because you mentioned about shielding, but
yeah, I think that's a good question. I think always. I remember, as I said, back in 2010 when we had the MIPI development, we unfortunately, I mean, fortunately for us, we do all our front-end modules these days are shielded. So back in those days, 2010, shielding was not really used as much. And there is another thing which helps us is the fact that all these new frequencies are in higher RF frequencies, 3.5 space or even higher, and typically the spurs are going low with the frequency in RF because the frequency spurs are the M harmonic of the clock for the MIPI. So it's much difficult to have a front-end module from the spur perspective, design at the frequency around 600 megahertz, for example, versus 3.5 gigahertz, due to the fact that that M for the harmonic, it's much higher, and definitely the power it's smaller, RF power is smaller. That works in our advantage. And for when it comes to millimeter wave, definitely the frequencies are quite high. That being said, there are other mitigations like being careful how the clock and the MIPI pins interfaces are placed on the front-end modules. We I think all the companies are taking care, very careful about that stuff.
Okay, I think we have room for just one last question that seems more of a comment than a question. I will just read it. In addition to speed, RFFE has added many options to help in scheduling with triggers. To avoid speed increases, which will impact cost technology without further increasing speed, it seems more of a comment than a question. I don't know if you would like to elaborate on that or want me to read it again.
Yeah, I think probably the question is definitely we have and I think I alluded a little bit, we have a lot of functionality which sometimes increase the size of the front-end module, especially CMOS and SOI. We have to think that we don't work into these technologies like 7 nanometer, 14 nanometer. I think as the technology evolves and the semiconductor prices are going down, hopefully this was not the case in the latest years due to other reasons. Probably we're going to migrate to lower feature nodes, which is going to allow us to have more functionality placed into front-end module. Unfortunately, we are not at that stage, despite the fact probably 5, 6 years ago, 8 years ago, we said that probably going to move to lower feature nodes.
Yeah. Okay, and allow me a very last question. This is coming from me. It's a topic I'm quite interested. Do you see any major difference in the IoT modules and smartphones, in terms of RFFE requirements? Because sometimes IoT modules, they tend to be specialized for certain application. Do you see a difference there, or it's quite immaterial?
I think it's a little bit of immaterial. I think IoT being there are so many solutions, and depends who you ask what means IoT. It's a little bit of a broader market, and probably the standard should play a bigger role, but I don't see a difference between MIPI, RFFE, and IoT. Definitely, I think, yeah.
Okay, thanks. Okay, I think we can probably close the session here. If there are many more questions from the audience, just send it to us and we'll forward it to Floriner. That's it. Thanks again, Floriner. Thanks again to the people attending the session. And I pass now to Justin, who will do the closing remarks. Thanks.
Yeah, thanks Fornal, and thanks Michele. Appreciate it. Yeah, so with that, wanted to thank everyone for joining us for our live MIPI DevCon 2022. Big thank you to all of our speakers, media sponsors. Yeah, really some great engaging content from our speakers. I want to also thank our MIPI team and our DevCon committee for your continued help and outstanding support. So with that, I will officially close today's event. We hope to see you at our in-person event next year. We also have the member meeting for our contributing members next month. Until then, stay safe and take care, and we'll leave it at that. Thanks.